Hi guys, today we're going to be looking at ideal op amps. So we're going to be looking at this circuit right here where there's two op amps that are ideal. What I mean by ideal op amps, I mean that the current going into the positive terminal and the current going to the negative terminal of an op amp is equal to 0. And the voltage of the positive terminal and the voltage of the negative terminal are equal to one another. So this is just a general way of or characteristic of an op amp where the currents going in are equal to 0 and the voltages are equal to one another. So let's label the nodes for this circuit right here. So let's start with this node over here. Well, this node is grounded, so we could say, okay, well, this node over here will be 5 volts. We'll say this node over here is 1. And well, the ideal op amp says the voltage in the positive terminal is equal to the voltage of the negative terminal. So this also node is going to be 1. This node is 1 as well because they're connected. And this node over here is 1. Now let's look at this node over here. We'll say, okay, well, this is 2, this is 2, and this is 2. They're all connected. Now we'll say this node over here is 3. This is 3. Well, remember, the voltage of the positive terminal is equal to the voltage of the negative terminal. So this right here, this node over here is going to be 3 because they're both equal. This is 3, and this node over here is V out. Okay, so we labeled all the nodes. For this circuit right here, we actually want to find what V out is. The output voltage that's at the end of the second op amp. So we labeled all the nodes. Let's label the currents. So if we would label the currents, you could say the current is going this way of the 5K resistor. It's going this way of the 2K resistor. This way of the 3K resistor. Down the 10K resistor. Down the 2.5K resistor. Down the 10K resistor. Down the 5K resistor. Across the 10K resistor. We're just labeling the currents for now, just so we could apply nodal analysis to make it a little easier. Now the currents that are going in this branch over here of the inverting input and the non-inverting input, the positive and negative terminal, that is equal to 0. So we don't have to label currents here. We could say, okay, well, the current going in here is going to go to this positive for this terminal 1. It's going to go into positive terminal 1 and out to 3 because there's no current over here. So I'm just going to not cross it off, but I'm just going to draw a zigzag across it just so we know that we don't need to look at these curves here, just to make it a little easier. Okay, so for an ideal op amp circuit like this, we want to apply nodal analysis, and we only want to apply nodal analysis at the positive and negative terminals of the op amp. So for example, let's look at the positive terminal of op amp 1 over here. We'll say terminal 1, top. If we apply KCL, we could say, okay, well, the current going in is equal to the current going out. So we could say, okay, 5 minus V1 divided by 5,000 is equal to V1 minus V3, right, going to 1 out of to 3 divided by 2,000 ohms. Okay, so we have this equation here. Let's simplify that equation a little further. So we could say, okay, well, 5 divided by 5,000 is equal to V1 1 over 5,000 plus 1 over 2,000 minus V3 1 over 2,000. Okay, so we isolated for, not for terms, but we put the terms together to simplify it a little bit. We could say, okay, well, this is one big term, this is another term, that's by V3, and this is a term on its own. Okay, so we simplified it. I don't want to calculate these numbers right here because we could actually just put it into the calculator and it will do that for us, just to make it a little more easier. Okay, so now let's look at this node over here. 1, and we'll say bottom. This node over here, we could say, okay, well, the voltage going in equals the voltage going out. These two, the current going in equals the current going out. And these two currents of this node over here, one bottom, they're both going out. So we could say V1 minus 0, because it's grounded, divided by 5,000 ohms, plus V1 minus V2 divided by 10,000 ohms equals 0. Okay, so now let's collect like terms and simplify it a little bit. So we could say V1 1 over 5,000 plus 1 over 10,000 minus V2 1 over 10,000 equals 0. So collect like terms, and we have two nodes of the non-inverting and the inverting input of the first op-amp. Okay, now let's look at the second op-amp over here. So this is going to be node 3, top. Node 3 at the top, we could say, okay, well, the current going in here is going to be the current going out. We don't look at this because remember, this current is 0, right? The ones with the squiggly lines that I put here is the current is actually 0. That's just that's the characteristic of the ideal op-amp. So let's look at this node here, node 3 at the top. We could say V1 minus V3 divided by 2,000, right, going in is equal to the current going out, which is V3 minus V0 divided by 3,000. Again, let's collect like terms. So we collect like terms, we end up with V1 1 over 2,000 minus V3 1 over 2,000 plus 1 over 3,000 plus V0 1 over 3,000 equals 0. Okay, so we collected like terms. So let's look at this node over here. That's the bottom of the second op-amp. So 3 bottom. Remember, the current going in equals the current going out. So at the bottom we have V2 minus V3 divided by 2,500 ohms. This one over here is equal to V3 minus 0, the ground, divided by 10,000 ohms. Okay, so we got that. Let's collect like terms again. We get V2 times 1 over 2,500 minus V3 1 over 2,500 plus 1 over 10,000 equals to 0. Okay, so now we have 4 equations and we have 4 unknowns, right? So we have equation 1, equation 2, equation 3, equation 4. The 4 unknowns is V1, V2, V3, and V0. In these 4 equations, we could actually just use 3 of them to find the V1 to V3 voltages. So if we look at one top, we see, okay, well this equation has V1 and V3. We look at one bottom, this one has V1 and V2, and we look at this one over here, V3 bottom, which is V1 and V3. The 3 top one actually has the V out, right? So we don't want to use this equation. We have 3 unknowns now, so V1 to V2, V3 with 3 equations, so we're able to solve for it. So let's put that all together. So if we look at these equations again, so we have V1, 1 over 5,000 plus 1 over 2,000 minus V3, 1 over 2,000 equals 5 over 5,000, right? We have the other equation, which is V1, 1 over 5,000 plus 1 over 10,000 minus V2, 1 over 10,000 equals 0. Well, this is running out. So let's use this. Okay. And then we have the third equation, which is V2, 1 over 2,500 minus V3, 1 over 2,500 plus 1 over 10,000 equals 0. So now we have 3 equations and 3 unknowns. So again, if we have a calculator out with us, we could plug it into the calculator. What we have to do is we have to hit mode 3 times. So I'll write that down. Mode 3 times. We hit equation. And we hit 3 unknowns. This will prompt us to put in A1, which is here, A2, A3, A4, A1, B1 to D1, and then same with this one over here and this equation over here. If we use that in the calculator, we actually end up with V1, V2, V3, that they're equal to -2 volts, -6 volts, and -4.8 volts. Okay, so now that we solved for these nodes over here, we could go back to the 3 top over here. This nodal equation actually has V0, and we want to solve for V0. And it has V1 and V3. So we could put this all together. So we could say, okay, well, -2 times 1 over 2,000 minus V3, -4.8, 1 over 2,000 plus 1 over 3,000 plus V0 is 1 over 3,000 equals 0. So if we solve and isolate for V0, V0 ends up being equal to -9 volts. So that's just a simple way of solving in the output of ideal op-amps. A circuit that looks like this. Just to remember that these over here, these lines over here, these ones actually have current that is equal to 0. So we don't put these in the KCL or nodal equation. And the voltage of the positive terminal is equal to the voltage of the negative terminal. And also we want to write the nodal equations just for the input of the positive and input of the negative terminals for both of these op-amps. Once we do that, we're able to find nodal equations, and then we find 3 of those equations that have like terms, and we put it into the calculator. We're able to solve for the nodal V1, V2, and V3, the node voltages, and then once we do that, we're able to find what V0 is, the output of the second op-amp. So yeah, this is just a a simple example of a circuit with ideal op amps. And yeah, thank you. Let me know if you have any questions. Leave it in the comments there. Thank you. Bye.